Welcome back, everybody. We continue with part 2 of the mini course on non-linear Grassmannians and flag manifolds. Presenting will be Cornelia Vizman from the University of Timișoara.
Thank you, Vienna. So lecture 3 and 4 will be done by Stefan Haller. So this is my last one, and I will do what I initially was planned for the first lecture, but it was not reasonable planning. So now I will talk about the coadjoint orbits that are modeled on nonlinear Grassmannians. So I will. So this is my motivation to study nonlinear Grassmannian, and so the plan is to keep a bit of the theory of dual pairs, but dual pairs of Poisson maps, but in a very special case, that one that we are interested in, coming from the two mutually completely orthogonal actions of two Lie groups, Hamiltonian actions of two Lie groups. And then I will present the ideal fluid dual pair. It's of this type. And then by doing reduction on one leg, we will get coadjoint orbits for the other group. And in this way, we will get coadjoint orbits of the Hamiltonian group. Reduction at 0 will give weighted isotropic Grassmannian, and then the reduction at something totally non-degenerate, the symplectic one will be giving the symplectic nonlinear Grassmannian. So, the first one is a decorated one, and then the second one is without decoration. And then I will talk a bit about, not entering too much into details, for the group of volume preserving diffeomorphisms. And here, these don't come from a dual pair. It's the classical one of codimension 2 nonlinear Grassmannian, vortex lines in R3, for instance, or vortex points in R2. And then it's this is work in progress with Francesco, the codimension 1. Here is a decorated nonlinear Grassmannian, and we'll see what the decoration is. So this name, long name of mutually completely orthogonal actions, this comes from the book of Lieberman and Marl. So I don't write the title anymore. You have that. So it's this definition. MCO, mutually completely orthogonal actions, on the possibly infinite dimensional symplectic manifold. In our case, it will be the manifold of embeddings. Manifold. Consists of commuting Hamiltonian actions, commuting Hamiltonian actions. So one is from the left and one is from the right. It gives H and G. The orbits are symplectically orthogonal. This means that the GM, so this at the point X, this is just the tangent space to the G orbit. So it is generated by all the infinitesimal generators, evaluated at some point. I should write at X, but I don't. And this is fracture H is the algebra of the group H, and then this is the tangent. At some point, X is the tangent space to the H orbit, and they are orthogonal, significantly orthogonal, and we learned already Topias and also in Daniel's lecture that in infinite dimensions we don't. In finite dimensions, we can take the symplectic orthogonal, and then we get also the vice versa identity. But in infinite dimensions, we have to assume it because it might be and vice versa. So a finite-dimensional example is when G and H are matrix groups. With Paul Scarif, we wrote a paper on, and we have these three examples. One is with the unitary groups acting on, but I've chosen one that is more like the analog of the actions for the ideal fluid dual pair. So, example, so this is from my paper with Paul Scarif. So here we have matrix groups. So the symplectic manifold is given by those matrices of dimensions 2n times m, which are of rank m. It's kind of the analog of embeddings. So here we have the action of the symplectic group SP2NR, and on the right the action of the orthogonal group OM, and the symplectic form here is the natural one. So we take trace of E times this. I will double J, so that our momentum maximum will be J2. And so this is a symplectic form on this space of matrices. And this subgroup of Gn to R to N and this of GLN, one can easily see the biggest subgroups which preserve the symplectic form omega. And maybe I will go further with this example. We have momentum maps, and the left group, it is transpose and J. This is after identifying the dual of the algebra SP, and then the right one.
Cornelia. Peter Maker says that F should be transposed.
Which one? Here, yes, thank you.
And the writing for the indices, it can still be quite difficult to read, unfortunately, for us. So
thank you. I will write the thank you. So it's E transpose J. and they form a dual pair on this symplectic manifold, and this is in general true. If we assume that in this MCO setting, the Hamiltonian actions have equivariant momentum maps, we will get a dual pair in the sense of Weinstein. Because there is also a notion of Hove dual pair. And there are in a paper of James Montaldi and collaborators, they study under which conditions the two notions of Weinstein dual pair and Hove dual pair are equivalent. So, assuming the existence of equivariant momentum maps, we need this equivariance in order to get them as Poisson maps of equivariant momentum maps. So this is in the context of the first definition. So it is denoted by GL and GR from the left H action. So it goes into the dual of G. And assuming this, one gets a Weinstein dual pair. Momentum maps of Poisson maps. What does it mean? That the kernels of the momentum maps are symplectically orthogonal to each other. So kernel of are orthogonal, the symplectic orthogonal of the kernel of PGL, and vice versa, because we are preferring for infinite-dimensional examples. Why is it like this? We know that the kernel of the momentum map is the orthogonal of the tangent space to the orbit, and so here on the left we will have the double orthogonal. This contains maybe strict inclusion. In any case, we have the implication. So we have from the MCO, we get a dual pair, not necessarily in the other direction, because here it might be different. A counterexample is the dual pair for three boundary fluids. It's in a paper with Francesco. For the other inclusion, so a dual pair of momentum maps that doesn't come from, that doesn't satisfy this orbit orthogonality. So the Hopf dual pair is the condition for this to be a Hopf dual pair is that the functions, so it's in general when he is a Poisson, here on the legs we have two Poisson manifolds, and then the condition, the Hopf condition, I'm sure I'm not pronouncing it correctly, but is that the Poisson subalgebras of functions that come from the legs, and the one from the right, they centralize each other. So in the simple centralize each other. The Poisson metric induced from the symplectic one. I forgot to say what is the Poisson structure we consider here. It's the Lie Poisson structure on the dual of a Lie algebra. Okay, so this was about mutually completely orthogonal actions, and now we will consider the action of the Hamiltonian group on the left, and here on the right will be the group of volume preserving diffeomorphisms. So we start with a manifold endowed with the volume form and with the symplectic. We will put the symplectic structure on the space of the matrix. Two steps. And the condition that the momentum maps are equivalent will force us to pass to central extensions. So the central extension, here which central extension that appeared already in Leo's talk. Here. So the second part, ideal fluid dual. So instead we need a manifold with the volume form. Manifold with the symplectic form. I will take the case when they are closed, it means compacted without boundaries, so the diffeomorphism group is so we don't have to take compactly supported diffeomorphism. So mu is a volume form, and omega is a symplectic form. So we will have here the group of diffeomorphisms that preserve the volume, the group of volume preserving diffeomorphisms. This will be the group G, acting from the right. So with the algebra of divergence-free vector fields. And here we have the Hamiltonian group, was already defined in this conference. And the algebra will be the Hamiltonian vector fields on M, but because M is closed, we can identify it, and we will, with the algebra of functions with the zero integral over M with respect to the Liouville volume form of the symplectic manifold. And in order to get the ideal free dual pair, we have to assume that that H1 of S is zero, unfortunately. So assume H1 of S. So in this case, every divergence-free vector field is exact divergence-free. So the algebra of divergence vector field consists of vector fields defined with a potential alpha. So alpha is k minus 2 form on S. So dimension of S is k.
Cornelia,
Yes.
what is written as a subscript for C infinity M?
Is 0, which so we have the zero integral functions. So to a Hamiltonian vector field, we can assign the unique Hamiltonian function that has zero integral over M with respect to the Liouville form on the symplectic manifold M. Equals 0. Equals 0. Thank you.
All right, thank you.
And similarly to the definition of the Hamiltonian vector fields of contraction with omega is dH, is the definition of the vector field with the potential alpha. So the contraction with the volume form is the alpha. This is the definition. Because H1 is 0, so every k minus 1, every closed k minus 1 form is an exact one. So that's why we have this identification. And so we have the Lichnerovich central extension, which CR, Claude Roger, he has a proof in one of his papers. We are still not 100% convinced that, so it's not rigorous enough for our taste. So we do hope to get more another proof that this is our work in progress. So so here Roger conjectures that it is universal. It is we take all the potentials, so k minus 2 forms on S. And we factorize them by the exact one, the omega k minus 3 of S. And here we assign the divergence vector fields to those potentials. So we go into G, and the kernel closed k minus 2 forms modular exact one. So here we have hk minus 2 of SR. So this is the plot by GPEC, central extension of G. What is the bracket? Classes of potentials. The bracket of two classes is the class of contraction by divergence free vector fields with the volume form. Now what are the actions? First, what is the symplectic manifold embedding? So out of omega and mu, out symplectic form. Am I writing big enough now for the online audience, or shall I make more effort? One bigger, Joel.
Thomas Strobel says it is somewhat better.
Okay. Oh, it was the first lecture. I think I was more nervous and I was writing more with stronger pushing on the blackboard.
I think that the light reflecting off of the top of the blackboard is sometimes a problem. When the top blackboard is all the way up, the light kind of reflects off of it, makes it hard to see.
Okay, thank you. So
yeah, so maybe if the top blackboard is just slightly down, it does a little bit better, I think.
Yeah.
But no, it was already okay just now. You had lowered it enough.
So now we have mutually completely orthogonal actions on the manifold of embeddings from S to N. What is the symplectic form? Let me put here also the symplectic form with omega. So we've seen last lecture that the tangent vectors at an embedding phi are vector fields on M along phi. So we insert them in the symplectic form and we integrate over S with the given volume form. So here x phi, y phi, tangent vectors of the space of embeddings, these sections of phi star Pm. And one can prove it is closed and not degenerate weakly, so it's a weak symplectic manifold. This is the space of embeddings, model of a Francesco space, and we have the actions now. As I said, on the left it is the group of Hamiltonian. He would have liked only needed only a symplectic action. We could take the symplectic group, and here we take the group of preserving the diffeomorphism. And if H1 of S wouldn't have been 0, we should have restricted to the exact divergence-free vector fields. And so the action is just here, the diffeomorphism F composed with the embedding phi, and here is the embedding phi reparametrized by the diffeomorphism G. And they have, the actions are Hamiltonian with the equivariant momentum maps. So first for the left action, GL, the left momentum map, at some point phi, an embedding, and then an element in the Lie algebra, which is a zero integral function, is simply integrating the pullback of the function to S with the volume form. And on the other side, the right one, at some point phi, and here theoretically we should put X alpha, but but the momentum map depends on the choice of potential alpha for the vector field, and since we don't have such a nice possibility to choose it, that's why here we have, in order to get it equivariant, that's why here we have to take the class of the potential, which is an element in the Snerovich central extension. And now they will be really equivariant momentum maps. So they are Poisson maps, and we can write the ideal fluid dual pair. They are really MCO actions for the condition to prove that the group of volume preserving diffeomorphism acts transitively here. One doesn't need the on level sets on of I will write first the so ideal fluid dual pair. So, how much time? 1:15. 1:15, so it's already 1:30. Speed up. Write the ideal fluid dual pair. So left and right equivariant momentum maps. So here goes into H star, which means the dual of it's a kind of so densities on M restricted to zero integral functions, and indeed one can formally write as the push forward of the volume form on S to a density on M. And if you look this could be written as the push forward phi star mu paired with H. And on the left side, so here, so this is H star, and here we have G hat star, which can be identified with the closed two forms on S, because I erased it, because it's the dual of K minus 2 forms modulo exact. We take the dual, so the regular part of the dual is given by two forms, wedging and integrating over with the volume form, and since we mod out the exact one, then we need closed in order to vanish. And this left, right one is pullback of the two form synthetic form omega, and this you can see from here compared with the alpha. So it's a dual pair, and what we have here on the right, we've seen yesterday Klebsch representation for in Tobias' talk, and it was something like he had the two functions, lambda and psi, functions on the manifold. So together they give function an R2 function of on the volume manifold, and then he assigned the vorticity to form d lambda wedge d psi, and it's the vorticity written in Klebsch variables. But this one can, so this would be our phi, and this would be simply phi star of omega. What is the synthetic form on R2? Yes, UI. So what we have here is actually a Klebsch representation of the vorticity. So here in the here is the space where the vorticities live. A bit more about this in point 4. When we discuss coadjoint orbits of diffball, okay. So this is the ideal fluid.
Cornelia?
Yes.
Could you just explain a bit how it is related to the fluids?
The fluids, yes, because of this Klebsch representation. So here on this, if you can see in the Lichnerovich extension. So if S is, for instance, if H k minus 2 of S is 0, then we don't need here to pass to the Lichnerovich extension. And then here on the leg down would be the dual of the divergence-free vector fields. And this is
no, but just more basic. It's fluids moving in which manifold? S, M? What is S? What is M?
M is no, here for the fluid we don't need M, so M will be so the name, the ideal fluid dual pair comes from the right leg.
Okay.
And then because here down in this special case we will have, so G star And this is the and identified with in that case it will be the closed one would be exact ones, and this is the space of vorticities. The vorticity if V is a divergence in vector field, then we assign, so with the metric we have the one form, and then the differential of V flat. This is the vorticity, and this is here in G star. And so GR gives a Clebsch representation for vorticities. And depending on M, one has, but as we see, the classical one is when M is R2, we get the classical Clebsch representation. And, but as you can imagine, if we don't have embeddings for bigger dimensional S. But this here does the name come from.
Okay, thank you.
Thank you. So we can go to the third point. Now there is a general principle that by doing a reduction in such a dual pair, we get conjoint orbits. So now we will do reduction in this ideal fluid dual pair. Under C, conjoint orbits, Wolf. So first we do reduction at 0. So what is GR? So here we will do reduction. So the pre-image, the pre-image of 0, the level set of 0, which consists of isotropic embeddings, so phi star omega is 0, and then we factorize by the group action. Ismagilov, he constructed a group that integrates the Lichner-Orbit satellite extension, but we don't need, because anyway the action comes from the action of the diff vol of G. So reduction at 0 gives us, again, prepared from yesterday's lecture. So we've seen these are isotropic embeddings, so because phi star omega 0 in the 0 level set, factorized by the group, which is the group of diffeomorphisms preserved in the volume form. And if here we wouldn't have had the isotropic ones, then we would get the decorated Grassmannian from last time, the weighted Grassmannian. But now we need also isotropic ones. So, and the general principle would say that this is a quadjoint orbit. Actually, we have to take, we will take the 0, the connected components, and they will, all of them will be quadjoint orbits of the identity component of the other group. No, sorry. Because the group H, the Hamiltonian group, is connected, quadjoint orbits are connected, so connected components of this will be conjoint orbits. To write the KKS symplectic form is good to write it as yesterday with as an associated bundle. So we can write it as isotropic embeddings cross here we work mu is a volume form. One could work as well with densities. I write them as here. It's the orbit, the mu orbit in the space of densities, and associated to the difference action. And now here on this Cartesian product, we can write a closed two form. Yes, and now it comes something that I didn't have time yesterday to finish. I will explain why the tangent space to that orbit, mu orbit in densities is given by exact k-1 forms. This is so this comes from it's really the reduced symplectic form. It's one just to do some computations. So at alpha, so this is in a pair phi, and I will denote by maybe it's better not alpha. It's at phi mu. So it is one term that involves the density mu in the orbit, and then we have other two terms. Contraction of x phi with omega is and the pullback is in is a closed one form. Sorry, omega. It's a closed one form, but because we had the H1 of S condition, the closed one form is exact. So here doesn't matter. It doesn't depend on the choice of gamma, such that the gamma is here this exact form. So. And then the same symmetric one minus this, the other one. So and this closed two form. So this is closed two form in the product, Cartesian product. And it descends. It is diff S basic. So the kernel is generated by the infinitesimal generators of diff S. So it descends to a symplectic form. So this descends to the KKS form on the conjoint orbit here. And yes, let me explain here why it is d lambda. So we have the map that assigns to every densities, but we think the thing here about the volume form. So it goes in the HK of S. And so it just takes mu to, or in general, a mu to its class. And one can see that the orbit of mu is the image of the orbit of its class in H. In the cohomology group, orbit which is finite. orbit. I explained yesterday the case when S is connected, but if S is not connected, then one has here a finite set.
Cornelia,
Yes.
I'm a bit confused. So why is the Hamiltonian reduction a coadjoint orbit? I missed this.
So here in a dual pairs of that come from mutually completely orthogonal actions. So in different, there is explained, for instance, in a paper of Ballet and Würzbacher. With Francois, we worked out a setting that is suited to this infinite dimensional one, when possibly we don't have a Lie group that integrates the Lie algebra in infinite dimensions. So there is that's why I say it's a general principle that in such dual pairs one gets coadjoint orbits, but of course, like usually in infinite dimensions, one has to really check in the setting.
But it's the coadjoint orbit of the other leg, or what?
Other leg, exactly.
Because you wrote diff vol, so that confuses me.
Ah, I wrote, sorry, where I wrote. So it's a
The title.
No, thank you.
Ah, okay, now, okay.
This is the number 4 with before. Okay. Thanks.
Okay, thank you.
Okay, so because it's the preimage of a finite set, so the tangent space to the orbit is the space of so the tangent space of mu to such an orbit. Omega k minus 1 of x. So here that's and the tangent space is the embedding vector space along phi. So these are the coadjoint orbits that Weinstein had for in the case of Lagrangian embeddings, and then was a PhD thesis of Lie. And where they get it, but not with the dual pair, and with Francois we get it in the dual pair. One can say also what happens when it is not 0. Then I said that the problem was here that if phi is an embedding, by differentiating with the condition phi star omega is 0, one gets that this one is a closed one form. And we want it to be exact in order to the thing work, that the transitivity works, the transitive action of the Hamiltonian group on this decorated Grassmannian works. And then one has to pass to what Weinstein calls isodrastic distribution. So we will have to restrict to isodrastic leaves. So they are really given by the condition that these are exact forms, not just closed. And then it works also when H1 of S is not 0. How many minutes? So now we do a reduction of the, I don't think I will have time for the group of volunteers with isomorphism, but you can ask me. So I will do now a reduction at the non-zero, a symplectic sigma. Maybe Stefan will say some words in his talk about this map H in the case of in the setting of non nonlinear flags, weighted nonlinear flags, because the quadrant orbits I just presented are can be generalized to the nonlinear flag manifolds. So when we do reduction of symplectic sigma x, which is the dual. So we come back to our dual pair. Now here we take a symplectic sigma. So the level set will be given by embeddings with phi star omega is sigma. So there will be symplectic embeddings of S sigma into M omega. And to be to make things easier, we will assume that mu is the volume form for sigma. So let's say that S is 2-dimensional, so mu is sigma to the power k. And now we do reduction. So it's the image of sigma, and we need the isotropy subgroup G sigma. What is G sigma? It's given by volume preserving diffeomorphisms, which also preserves sigma, but because mu is the Liouville form, so here what we get is simply the symplectic group of S. So see, that's why we will get Grassmannians, not decorated Grassmannians, because the decoration doesn't count anymore. So we will have those embeddings, these symplectic embeddings from of the symplectic manifold S to the symplectic manifold M, and factorized by the symplectic group. So what we get is the symplectic Grassmannian of the Grassmannian of symplectic manifolds of M of type S sigma. But this type actually doesn't play a role, because again we will take connected components. So actually what we have is the symplectic Grassmannian, which is open in here. It's open in the Grassmannian of all submanifolds. It is a union of such. We just have to see which type it is. We call it sigma, and then so that's why the theorem, which is from our old paper, which Stefan from 2004, that every connected component of the symplectic Grassmannian is a coadjoint orbit of the Hamiltonian group. But then we checked it directly without the dual pair. Every connected component. Let's see. Coadjoint orbit of M. What is the symplectic form? The KKS form. It is, remember yesterday we talked about transgression. It is the transgression of the 2k+1 form omega k+1 So it's tilde. More precisely, one can, what does it do? It takes two normal vector fields. We've seen that a tangent space to the Grassmannian is the space of normal vector fields. And because this here is open, also the tangent space to the symplectic Grassmannian is given by such. And then simply integrating over S, contraction of this form. Just like we find the transgression, but if one gets actually a factor, so it is omega 1, 1, 1, 2, integrating with the 2k form, with the highest degree form on S. And now if one can look what happens when S is zero-dimensional, then one gets configuration spaces of points in M, and so it's coadjoint orbits. In particular, M omega is a coadjoint orbit of Ham M. Yes, so this is part 3, and how, no, so part 4, that's it. Thank you very much. Thank you very much for your attention.
Thank you for that. Are there any questions online? Yes, I see your hands. You can unmute yourself and just ask them. Or should I read?
Yes.
Is the symplectic reduction a coadjoint orbit because of the dual pair?
Or
Yes, it is. This was long ago.
Okay, well, in this case,
The answer is yes. The answer is actually yes, because of the mutually completing orthogonal actions.
do we have any more questions here in the audience present? No? Well, if not, this was all we had planned for today. Thank you, Cornelia.